Welcome, and thank you for standing by. I'd just like to inform all parties that your lines have been placed in a listen-only mode until the question and answer segment of today's conference. This call is also being recorded. If you have any objections, you may disconnect at this time. I will now like to turn the meeting over to your host, Ms. Rachel Kraft. Thank you. You may begin.
Okay, thank you. Hello, everyone, and welcome to today's teleconference on the lunar science secondary payloads flying on NASA's Artemis 1 mission. I'm Rachel Kraft with NASA's Office of Communications. Artemis 1 will be an uncrewed flight test that will provide a foundation for human exploration in deep space and demonstrate our commitment and capability to extend human existence to the moon and eventually Mars. The agency is currently targeting no earlier than Monday, August 29th for the launch of the Space Launch System rocket to send the Orion spacecraft around the moon and back to Earth. Today you'll hear from people who have developed and built CubeSats, small satellites that will ride to space inside an adapter ring on the rocket called the Orion Stage Adapter to primarily investigate the lunar environment. After the Orion spacecraft is flying on its own toward the moon, these shoebox-size CubeSats will be deployed from dispensers on the adapter ring. While CubeSats each come with risk to their own individual missions, they yield high potential to fill gaps in our knowledge of the solar system. We have several experts lined up to talk to you today. They are Jacob Bleacher, NASA Chief Exploration Scientist, Craig Hardgrove, Principal Investigator for the CubeSat LunaH-Map and a professor with Arizona State University, Tatsuaki Hashimoto, Project Manager for the CubeSat OMOTENASHI with the Japan Aerospace Exploration Agency, Ryu Funase, Project Manager for the CubeSat EQUULEUS with the Japan Aerospace Exploration Agency, Ben Malphrus, Principal Investigator for the CubeSat Lunar IceCube with Morehead State University, and Joseph Shore, Lockheed Martin's architect for small sat missions. Joseph will be talking about the CubeSat LunaIR. We'll have a few opening comments from each of our speakers, and then we'll take questions from reporters on the phone line. Reporters can enter *1 on your phone to be entered into the question queue. And with that, we'll start with Jacob Bleacher.
Thanks, Rachel. Can you just confirm you hear me?
We do indeed.
All right. Thanks, Rachel. And it's a pleasure to be here this afternoon to speak to everybody. We're at the beginning of an exciting adventure to explore the moon. But not only to explore the moon, to learn about our place in an evolving universe. Our moon serves as basically a celestial library right next door. From here, we can begin to research our history. Lunar rocks and lunar ice basically serve as the books of this library. We can use them to learn, to read them, and to begin to reveal how the solar system has evolved. This can really help us gain insight into what was happening here on Earth when life was establishing a foothold in the solar system. Here on Earth, the very characteristics that make life possible, for instance, our atmosphere and water, well, those are the same characteristics that tend to erase those pieces of our planet's history. However, at the moon, the same characteristics that challenge the existence of life are the same characteristics that have helped preserve evidence of our history. For instance, not having an atmosphere. Everything that's happened there has left a trace. But those are the traces we can't find here on Earth. Not only can we learn about our Earth-Moon system, but learning from the moon will help set the scientific context from which we can interpret our observations from across the solar system. Artemis 1 will test our spacecraft and hardware that we'll use to carry astronauts to the moon. Additionally, Artemis 1 will enable us to test the use of CubeSats as secondary payloads that can be delivered beyond low Earth orbit like most other CubeSats are. One of the great things about the payloads we'll be talking about today and on the remaining telecons that NASA will hold the rest of the week, it's the number of organizations both inside and outside of NASA that are coming along on this flight with us. Payloads or instruments on Artemis 1 reflect contributions from across our agency. They include 5 international partners, and partnerships with a number of universities and industry and other research institutions. CubeSats are a lower cost approach to capturing scientific measurements. They're high risk but high reward, and each successful measurement these Artemis CubeSats can add to our knowledge to the moon and how we travel in deep space. This demonstrates the collaborative nature of science and exploration. I often like to say that science is our toolbox for survival during exploration. These CubeSats will provide new understanding of the lunar environment, which in turn will help us better design our exploration systems, help keep our crew safe, and help hardware survive longer at the moon. So this really is an exciting time as we get ready for this adventure. Now I'm really excited to introduce a few more of our experts from several of the CubeSat teams. First, I'd like to hand over to Craig Hardgrove, Principal Investigator for the CubeSat LunaH-Map, and he's with the Arizona State University.
Thanks a lot, Jake. LunaH-Map was the first simplex mission selected through NASA's Science Mission Directorate. It's a new type of mission for NASA, but it follows a similar structure to previous missions that are much larger, where we have a PI that is a planetary scientist that proposes a large science question, in our case about the moon, and we execute a mission to conduct addressing that question. And so as the first simplex selection, we're really a pathfinder for navigating a lot of the challenges that come along with doing a big science mission on a very small satellite. And so we've known for quite some time that there's water ice at the moon's poles, but there are a lot of unanswered questions about how much there is and where exactly it is. Most of it is within these permanently shadowed regions at the South Pole. These are some of the coldest locations in the entire solar system, and they may have never seen sunlight. And it's the only place on the moon where we know that water ice really would be stable for prolonged periods of time. There's evidence that there may be ice within the sunlit plains that might be stable for millennia in those regions, but we simply don't have high enough resolution data of both poles of the moon to really address some of these questions. And so that's where LunaH-Map came in. And in order to do that, we're using a tried and true technique called neutron spectroscopy. NASA has actually flown 2 neutron instruments to the moon before, but with LunaH-Map, we're enabled, because we're one science instrument on such a small spacecraft, we're able to plan the mission and navigate into a very low altitude South Pole orbit so that we can pass over these regions of the South Pole and reveal whether or not there are enrichments of ice only within the permanently shadowed regions, or if the ice actually extends out into the illuminated plains. And this will tell us really important constraints about how water was delivered into the inner solar system, how much water was there at the moon's formation. It also tells us how water is redistributed across the moon from subsequent impacts and meteorite bombardment. So it's really an important element of the Artemis program to understand how much ice is at the pole, both for future exploration missions, both with humans as well as robots, to understand how to plan future missions at the scale of a landing ellipse, so we know where to go to find these ice enrichments, as well as uncovering sort of how the evolution of the moon evolved is with respect to water ice mobilizing on the surface of the moon. And I think I would end it there and just say, if you have any other questions or or information about LunaH-Map, we have a website at lunamap.asu.edu, as well as a new press kit, which will answer a lot of your questions and have some graphics. And with that, I'll hand it off to Tatsuaki Hashimoto with JAXA.
Thank you. I'm Tatsuaki Hashimoto from JAXA, project manager of OMOTENASHI. The name of OMOTENASHI comes from outstanding moon exploration technologies demonstrated by nano semi-hard impactor. Sorry for a long name. As the name shows, it is a challenge for the world's smallest moon lander. there is no room to be equipped with landing sensors or precisely control liquid propulsion system on a CubeSat. So, OMOTENASHI uses a solid rocket motor for the deceleration and adopts semi-hard landing technology, not soft landing. Its remaining landing speed will be around 50 meters per second, so we needed to develop shock absorption technologies, crushable material, and an epoxy filling of the instrument box. Moreover, to reduce the landing mass, the spacecraft separates in orbit just before landing. OMOTENASHI has also an ultra-small radiation monitor and measures the radiation environment of Earth-Moon region. It is remodeled from the portable radiation monitor developed after Fukushima nuclear plant accident. Its weight is about 20 grams. And OMOTENASHI itself is not a science mission, but its demonstrated technologies will enable future small surface science missions. And after launch, on the second day, OMOTENASHI will conduct orbital maneuver to put into lunar impact orbit. The trajectory is carefully designed so as to maximize the probability of landing success. The ignition timing of solid rocket motor is very important, so we will conduct precise orbit determination for a few days. On the 5th or 6th day, OMOTENASHI will land a moon. This is an overview of OMOTENASHI mission. And I'm going to pass on to the next speaker, my colleague, Professor Funase from EQUULEUS mission.
Okay, I'm Ryu Funase from JAXA, and I'm the project manager of EQUULEUS. So let me give you an overview of the EQUULEUS mission. EQUULEUS and also OMOTENASHI introduced earlier are JAXA's second mission to send a micro or nano spacecraft into deep space beyond the moon. So we are very grateful to NASA for providing us with this valuable launch opportunity into deep space. The primary mission of EQUULEUS is to expand the capability of CubeSat in deep space by demonstrating trajectory control techniques within the Sun-Earth-Moon region. In this mission, we aim to efficiently reach a periodic orbit around the second Lagrange point of the Earth-Moon system by utilizing lunar gravity assist and solar gravity. This orbit control technology will enable a CubeSat-class spacecraft with limited resources to depart from future deep space ports such as Lunar Orbiter Platform Gateway and fly into deep space with its own propulsion system. It will contribute to greatly expanding our opportunities for future science missions around the moon and beyond. To accomplish this mission, we developed and installed a new propulsion system using water as a propellant. Water is, an extremely safe and non-toxic propellant, and if this propulsion system is demonstrated, it will improve CubeSat's mission capability and ensuring safety for various future rideshare launch opportunities. In addition to the technology demonstration mission explained so far, EQUULEUS will conduct 3 other scientific observation missions. One is an imaging mission of the Earth's plasma sphere, and from a far distance from the Earth, EQUULEUS will observe the whole view of the large structure of helium ion in the Earth's plasma sphere. This will contribute to the better understanding of the physical process which governs the terrestrial plasma of the Earth. The second is a mission to image and characterize the lunar impact flashes. This observation will monitor the moon surface and detect the flash of light emitted by the high-velocity meteorites which impact on the moon surface. And this mission will characterize the flux of such meteorites in order to contribute to the risk evaluation for the future human activity or infrastructure on the moon's surface. The third one is a mission to detect cosmic dust and evaluate the dust environment in the cislunar space. This observation is made possible without the need for extra resources from the spacecraft by integrating thin film dust detectors into the inside of the spacecraft thermal blanket. In addition to the tech demo mission to enhance the capability of deep space CubeSat, as I explained earlier, these three science missions are expected to deepen our understanding of the radiation environment around the Earth, and also the spatial distribution of the solid objects such as meteorites and dust in the Earth-Moon region. This is an overview of EQUULEUS mission, and I'm going to pass on to the next speaker. So please.
Thank you, Professor Funase. This is Ben Malphrus, the principal investigator on the Lunar IceCube mission. CubeSats are going to the moon. It is such an exciting time. We really feel like we're at the beginning of a new era of space exploration, one that's ushered in and supported by small satellite platforms like these CubeSats on the Artemis mission. Lunar IceCube is a partnership between Morehead State University, the NASA Goddard Space Flight Center, the Jet Propulsion Laboratory, the NASA Independent Verification and Validation Center over in West Virginia, and the BUSEC Space Propulsion Company. Like the other CubeSats on Artemis 1, Lunar IceCube is a 6U CubeSat, 14 kilograms or so, about the size of a carry-on piece of luggage. And the science mission for Lunar IceCube is to prospect for water ice. The interesting thing to me is that along with LunaH-Map and others on the Artemis 1 mission, we're creating really the first ad hoc lunar constellation of satellites that are targeting common observations, common targets, and producing very complementary science data. Specifically, Lunar IceCube is looking for water ice in liquid and vapor forms and other lunar volatiles we have the sensitivity to see. But specifically looking at the distribution of water ice from the mid-latitudes to the PSRs, the permanently shadowed regions, where it tends to collect. So Lunar IceCube is actually a science mission and a tech demo mission. There are a number of really innovative, unusual technologies that are sort of enabling technologies that allow us to do this kind of science with small platforms. The instrument is a very innovative instrument built by NASA Goddard. It's an infrared spectrometer. We call it the Birch's spectrometer. Has excellent sensitivity in the 1 to 4 micron range, where we'll see the water ice line in absorption. There are other technologies like an electric propulsion system, very innovative propulsion system. It's an RF ion electric propulsion system developed by BUSEC. And there are a number of other enabling technologies. But together, with the infrared spectrometer and these other enabling technologies, we hope to contribute to some of the unknown elements of the strategic knowledge gaps related to the moon and lunar volatiles. So with that, I will turn it over to Joseph Shore from the LunaIR team.
Thank you, Ben. We're looking forward to the Artemis 1 launch, not just to return astronauts to the moon, but to start building up an eventual full-scale lunar economy. CubeSats like LunaIR and other spacecraft on this call today are a new and different way to learn more about Earth's nearest neighbor and what challenges it could pose for future human missions. They're also an opportunity to prove out technologies that could be useful for future lunar science. So I'd like to talk briefly about Lockheed Martin's CubeSat catching a ride on the Artemis 1 mission, LunaIR. The LunaIR project is a public-private partnership through NASA's Next Space Technologies for Exploration Partnerships, or NextStep program. NextStep is run through the Advanced Exploration Systems group at NASA and is focused on technology demonstrations. LunaIR is one of these. It's short for Lunar Infrared, and For its technology demonstration mission, LunaR aims to conduct a flyby of the moon and prove out an ultra-compact novel infrared camera by taking a series of images that observe the lunar surface and its thermal signatures. What makes this imager particularly useful is that it can map the moon in both day and night and measure things like the way sunlight is reflected or absorbed by the moon's surface. We're hoping to see how well this imaging technology works so that it might be applied for things like future planetary scouting missions. And in addition, the types of thermal data LunaR would look for could eventually be critical in helping identify water on the moon, which in turn drives selection of things like future lunar landing sites or outpost locations. One of the challenges that these lunar CubeSats face is packing a lot of technology into a very small volume. And one example on LunaR is that infrared sensors typically need to be accompanied by a cooling system so that they give good performance in the images they return. And because of its compact size, LunaR has the lightest long-life space cryocooler ever built by the Advanced Technology Center in Palo Alto. This is an example of just one of the types of challenges that we have to engineer for on these high-risk, high-reward missions. So LunaR was funded by Lockheed Martin with the launch provided by NASA. Lockheed Martin's Optical Payloads Center of Excellence in Sunnyvale, California, built the infrared imager, and our Advanced Technology Center in Palo Alto, California, built that cryocooler that I mentioned. The LunaR 6U CubeSat bus was built, tested, and integrated by Terran Orbital in Irvine, California. And on the whole, Lockheed Martin is really excited to be part of NASA's efforts around the moon, from designing, building, and testing the Orion spacecraft to proving out new technology with LunaR, and even participating in future lunar imaging missions like Lunar Trailblazer and beyond. So I'm eager to see how what we learn now with all of these missions across the different size classes can be applied as future lessons learned when humanity has a growing number of assets at the moon. Thank you, and at this point I'll pass it back to Rachel.
Okay, thanks. We'll now begin the question and answer portion. As a reminder, you can enter *1 on your phone to be entered into the question queue. Your phones are on mute now, and the operator will open your mic when you're ready for your question and close your mic after you ask your question. And we ask that you please stick to one question each. And given that we have a number of speakers on today's call, please identify to whom your question is directed. If we do have time, we'll allow reporters to ask a second question. And we will start with Megan Bartels with Space.com. You okay?
Megan Bartels, your line is open.
Can you hear me okay? Hello?
Hey, Megan, we can hear you. Right
okay, great, thanks. Could each of the panelists representing a specific CubeSat state the planned primary mission duration for the CubeSat and any key milestones we should be looking for? Thanks.
And for that, I think let's go in the order of the speakers. So Craig, let's start with you.
Sure. We deploy, the LunaMap deploys from SLS about 5.5 hours after launch. We should have a first contact from the spacecraft within about 30 minutes of deployment. Beyond that, we will spend about the next 4 or 5 days performing a lunar gravity assist to fly by the moon. If we successfully hit that gravity assist, we go out to about 1.5 million miles past the moon and back. That takes about 4 months. And then we transition, once we're captured at the moon, into a science orbit. That takes us about 12 months. So all told, our mission would be about 14 or 15 months long, with the last part, the science phase, being about 2 to 4 months long.
Oh, I'm sorry, I couldn't catch the questions exactly.
The question was about expected mission duration for each payload.
Okay. Okay. Yeah, as I already explained, yeah, OMOTENASHI's mission is about less than 1 week, about 5 days, like so. Yeah. After separated from SLS, OMOTENASHI change the orbit to impact to the moon and directly go to moon and land. And after landing, its lifetime will be about a few minutes because of the thermal conditions or something like that.
Ryu? On to you.
Yes. Yes. So EQUULEUS is the first CubeSat to be deployed from SLS Artemis 1, and just after the separation, we will have DSN contact path to where we will verify the health status of the spacecraft, and after that we will we will conduct the trajectory correction maneuver to target the spacecraft to our nominal trajectory. And after performing lunar flyby in a week, we will conduct the deep space flight to the lunar Lagrange point that will take about 1 year or so. And after that, we will enter into our mission orbit around the Lagrange point and conduct science missions, as I explained.
For Lunar IceCube, it's fairly similar to the others. We're more or less a 2-year mission. We get deployed at bus stop 1. 3 hours or so later, we have our first contact. We have a series of deterministic maneuvers to set us up for lunar flyby about 5 days after launch. But the interesting thing beyond that is we go on a long circuitous route using the interplanetary superhighway for about 180 days. We go as far out as 1.8 million kilometers from the Earth, and then we fall back to the Earth-Moon system in the right dynamic state to undergo a capture. We'll stay in the near rectilinear halo orbit for a TBD period of time, and then we'll dive into a science orbit. And, why does it take so long to get to the moon when, we go flying by the moon in 5 days? But we can only carry 1.3 kilograms of propellant, so you can't turn around and thrust in the anti-velocity direction to extract energy and go directly into lunar capture. So we go on this long circuitous route that allows us to utilize our low-thrust engines, extraordinarily low amount of propellant, and basically the laws of physics of the solar system to allow us to get into a lunar orbit. So you have to be a little bit more patient, but with a little over a kilogram of propellant, we can still get into a very appropriate science orbit that takes us about 100 kilometers, about way above the lunar surface. So thanks for the very interesting question.
Let's see, and Joseph, can you comment on mission duration for LunaIR?
Yes, I can. LunaIR is a pretty quick mission, not quite as short as OMOTENASHI, it sounds like. We are a lunar flyby, so after... sorry, can I ask if, can you confirm you're hearing me okay?
Yes, we can hear you.
Okay, great. Thanks. Yeah, we deploy from the launch vehicle about 6.5 hours after launch. We'll do some demonstration activities with our sensor pretty quickly after that, and then we fly past the moon, where we do most of our image taking of the moon, and then downlink the data from that. So it's a pretty short timeline. We are not planning for the mission to last longer than 30 days.
Okay, thank you. We'll take our next question from Jeff Faust with Space News.
Yeah, good afternoon. Pardon me. I know some of the missions are dealing with an issue that you delivered your satellites a year ago and haven't had a chance to recharge your batteries. I'm just curious what you're doing to try to mitigate the risk from the steadily discharging batteries and what that implies for mission success. You know, what the odds are you'll be able to carry out your missions. Thanks.
Yeah, this is Jake Bleacher. I can take that one. So, yeah, as you said, the space, each of these CubeSats was delivered a little bit over a year ago and were installed into the SLS stack. At that point, there were several that had the capability of being recharged, and then there were several that simply did not have that capability once we were stacked. At this point, it's difficult to apply any more charge to those CubeSats. So we're trying to work through preparations and get the SLS ready to fly. That's the best thing that we can do at this point. You know, the primary goal here is to fly the SLS and the Orion and check out that system, make sure that it will work and is ready to go for Artemis 2 when we'll have our astronauts on board. So right now, what we can do is, again, we had several that we were able to recharge, several that we are not. We are trying to monitor them, and if we get the SLS off the end of this month, early September, we hope that they'll all have an opportunity to be able to fly. But as we mentioned, CubeSats, you know, they're kind of a high risk, high reward, that reward coming from the fact that they're lower cost. And so, you know, as we develop Artemis, we're learning about how to partner with these types of capabilities. The kind of the size of these CubeSats, you heard several folks talking about, you know, some of the decisions that have to be made as you develop these CubeSats. You can't have everything in there that you would have in a full-size spacecraft, and choices had to be made to enable us to go and fly these things so that we can make the measurements. In that case, there's maybe a few that we can't get recharged. So again, you asked what we can do to mitigate at this point. Trying to get the SLS off the ground. That's the thing we can do to get these up there and get these CubeSats out so they can get themselves unfolded and get going.
Okay, thank you. We'll next go to Yusuke Tomiyama with Yomiuri Shimbun.
Thank you for taking my question. Can you hear me?
Yes.
Okay. My question is for Dr. Funase and Dr. Hashimoto. I know you have been waiting for this launch for a long time. So let me know your expectations for the launch now. Thank you.
Okay. Yeah. I couldn't get the meaning of the expectation, but yeah. We are now very exciting about just before launch, and yeah, and we are preparing for the in-orbit operation. Fortunately, we have a lot of time to prepare the in-orbit operation. So we have some confidence to do the in-orbit operation.
Yeah, and I'm Ryu Funase from JAXA, and as I explained earlier, this is the JAXA's second opportunity to send CubeSats or microsats into deep space. So we are very excited to have this wonderful launch opportunity into deep space. So yeah, we're very excited. to perform our mission successfully. Yeah.
Thank you. The next question is from Ramian Skiba with Wired.
Hello. I had a question about, just one second, for Tatsuaki Hashimoto. This is about the OMOTENASHI mission. I was just wondering, I think I missed it, but like, what is the advantage of making a semi-hard landing? Like, what is this useful for certain kinds of landers, like future possible missions?
Oh, okay, yeah. Semi-hard landing has, I can say, a little risky and many disadvantages here. But for such a small size CubeSat, we can select only a semi-hard landing, I think, because we have no room to both precise landing radar or a precisely controlled propulsion system or like so. So we need to take semi-hard landing. And yeah, semi-hard landing, we need some shock absorption technologies. So we cannot both very precise sensors, but usual electric circuit, for example, camera, infrared camera, or some science instrument will be possible to stand high shock G. So that enables future small surface missions, I hope.
Thank you. Our next question is from Marcia Smith with Space Policy Online.
Thanks so much. I don't know if Dr. Bleacher wants to answer this for everybody or if each of the CubeSat PIs would like to answer for themselves, but I'm curious, of these 5 CubeSats, which ones could not be recharged, and how much will that affect the possibility that they'll succeed?
I can answer that. And this is Jake again. I can answer that, and then if anyone else wants to add to that, certainly can. So yeah, 5 of the CubeSats had the ability to be recharged, and 5 were not in a status that we were confident we could recharge them. LunaH-Map is one of those. CUSP, Lunar IR, Team Miles, and the Lunar IceCube were the 5 that were not in a status where we were confident we could get those recharged, and or they chose not to have them recharged. As I said into the earlier question, monitoring them as best as we can. We believe that if we are able to launch towards the end of August, early September, which is our current target, that most, if not all, of these CubeSats will be able to become active after they are deposited from the SLS and Orion, but we'll have to find out when they get out there.
Okay, thank you. Our next question is from Stephen Clark with Spaceflight Now.
Hi, thanks for taking my question. Since LunaH-Map was one of the ones that was not recharged, I'll ask Craig about that. Why wasn't that particular CubeSat unable to be recharged, and do you have any concerns about that adding any risk to your mission? Thanks.
Sure, thanks for the question. Yeah, so that was a decision that came out of one of the reviews with the SLS program. So the SLS program didn't feel comfortable with us charging. And so that's why that decision was made. But I don't, it is a concern, like Jake said, these are high-risk missions. However, looking at our rate of self-discharge that we measured prior to delivery and moving forward with looking at the late August, early September launch, I think we should be in a pretty good position, just like Jake said. If we happen to be below the minimum state of charge required to boot our flight computer, we do have 2 exposed solar panels after we are after the dispenser kicks us out into space. And so those 2 panels will charge the batteries. And assuming that the batteries are not depleted all the way to 0, we should be able to charge those in not too much time after deployment. So all the CubeSats are in a slightly different situation, but for LunaH-Map, I think we should be okay with the launch coming up soon.
Thank you. Our next question is from Christopher Kokonis with Astronomy.
Yes, hi, thank you. I think we got a couple responses from the JAXA colleagues. So I guess this is directed, kind of sort of a 2-part question, first for Craig and Ben. How are you guys feeling right now? Like how much anxiety, hope, excitement? You could just give us a little sense of the human side of how you're feeling. And then I'm curious where each of the PIs will be physically located during the launch and during the CubeSat separation a couple hours later. Thank you and good luck, everyone.
Thanks for the question. This is Ben. I'll go first, but I think you described the mix of feelings with great precision. Hope, anxiety, excitement, happiness, all mixed together. It's it's been a long and fairly complex journey. These are some of the most complex CubeSats ever produced, and to get the performance levels that are required to do the science, we had to push the envelope. You had to take risks, and so we all as program engineers balance those risks against the science capabilities, and it comes down to a little bit of a gamble in the end. How much did you want to push the envelope in terms of toward what level of gains? And so that part's really exciting. We've had, 50 plus students working on Lunar IceCube over the 5, 6, 7 years of its development. And we have a lot of students and graduates now that are really excited to see it fly. So, a complex mix of emotions for a very complex set of small satellites.
Yeah, this is Craig. I'll just add to what Ben said. I agree with everything Ben said. I just add, it's been so great to get to know this community of scientists and engineers. I met Ben 7 years ago or so, and I feel like we have gone through a lot of the same struggles together developing these systems. And so I'm more than anything, in addition to all the feelings you mentioned, extremely excited and happy to have these projects move on to the next phase of their lives. For me, this is really like a third child. So sending it off to the moon and getting to see it have a chance at completing its mission is really a special thing. So.
And this is Joseph Shore from LunaIR. I'll just add to this that we hit a lot of major milestones in our integration and test and delivering the spacecraft to the launch site last year. And so kind of no matter what happens in the mission, we've already learned a lot. We've already had some major accomplishments, and we're excited to see the next phase of operations.
Okay, any others want to address that? Okay, we'll take another question. This one from David Curley with Discovery Channel.
Much for taking the question. Hashimoto-san, can you explain a little bit about the technology from Fukushima? And will that instrument record not just on the way down, but on the surface of the moon as well? Thank you.
Okay. Yeah. Unfortunately, we had a very, sad Fukushima nuclear plant accident. And after that, we need to monitor the radiation environment even for the school children. So the Japanese Institute developed a very small portable radiation monitor for the children. So after that, we JAXA started the research to use for that small monitor to the astronauts or such kind of small sensors can boost every spacecraft because it is a very low power consumption and a very small size. So our mission is test for such a tiny small sensors can detect radiation environment precisely or not. Yeah, that is another challenge. But if possible, we would like to spread such kind of a small sensor to every spacecraft to the moon or Mars or some destination. Thank you.
Thank you. We'll take another question from Irene Klotz with Aviation Week.
Thanks very much. I'm not sure who might be best or interested in answering this question, but you mentioned, a couple of you mentioned about the technology pathfinders that these missions are intended to demonstrate. So I was wondering, in the 6 or 7 years since these projects were initially selected to fly on SLS, which I think at the time it was supposed to go in 2018, have any of the technologies been surpassed or tested by other satellites and other programs? In other words, is any of the pioneering technology now moved on to a demonstration of a system that's already been previously demonstrated? Thanks.
I think that's an excellent question. This is Ben. I'll give a preliminary answer. And the short answer is certainly some technologies have evolved, particularly looking at our infrared spectrometer. You know, there are probably better small miniaturized cryocoolers available, for example. So certainly there have been some improvements there. You know, CubeSats are really good at demonstrating technology quickly in LEO, but almost no CubeSats have flown in deep space. The Marco CubeSats are really the exception, and then the Artemis 1 CubeSat. So most of the technologies are really designed for operation in deep space, you know, getting from one place to another in deep space, like the high ISP, low thrust propulsion systems, and some of the more rad hard systems. So those really haven't been demonstrated in the CubeSat form factor in an appropriate environment. So I think it's an excellent question, but I think there's still a lot of very valid tech demo to be done and many things to be learned technology-wise from these missions.
Yeah, and this is Joseph Shore from LunaIR. We are still interested in demonstrating the infrared sensor on LunaIR, but to your question, one element of that sensor, the micro cryocooler that I highlighted in my initial remarks, has actually made its way into some instruments on some additional missions. It's going to be part of the Psyche mission and the Europa Clipper mission. So while the development happened on LunaIR and we're anticipating that flight, we have seen the technology is already transferring into much larger missions.
And this is Craig with LunaH-Map. The neutron detector that we developed for LunaH-Map has a unique capability that is sensitive to both neutrons and gamma rays. And that technology has not flown yet in space, although it has been tested and for radiation damage and hardening. issues associated with that, and everything looks good. But we will be one of the first to fly this sensor material into deep space. And there are other sensor technologies that might have useful applications in the similar class for future planetary science missions, but so far, LunaH-Map will still be the first to fly that. And also just wanted to add maybe to Ben's point, the 6U is a very challenging form factor. It's incredibly small. And so, I hope that the success of many of these CubeSats on Artemis 1 demonstrates that these, that there should be future technology investment in propulsion systems and all the technologies that make these spacecraft go to enable future missions. So, looking forward to that, but I think that we're still very close to state of the art at this point.
Yeah, I'm Ryu Funase from EQUULEUS. Okay, can I speak?
Yes, go right ahead.
Okay. So the technical mission of EQUULEUS is the demonstration of the very efficient trajectory control techniques that enable a CubeSat to reach lunar Lagrange point with a few tens of meters per second. And I think this technology has not been demonstrated by other missions. So I think the technical mission for EQUULEUS is still valid at this moment.
This is Tatsuaki Hashimoto from OMOTENASHI. Yeah, the OMOTENASHI demonstrates semi-hard landing technologies, and that will enable the new science missions. So if lunar scientists who are interested in this kind of technology, we can cooperate with them.
Okay, thank you. And we have time for one last question from Marvin Marshall with Nighttime News Space Report.
Hi, thank you so much for taking my question today. Good evening. My question goes out to the Lunar IceCube mission team here. Now, you guys said that the goal is to pretty much investigate the distribution of water and other volatiles on the surface of the moon there. Now, are you guys looking into finding any type of propellant for future rockets or landers that might be landing there? Thank you.
Oh boy, that's an excellent question. Of course, many of us have an interest in situ resource utilization, and water, of course, could be ultimately harvested on the moon and disassociated into oxygen, which is an oxidizer, and of course has other valuable uses, and hydrogen. So in theory, you could certainly create both a propellant and an oxidizer out of the water ice on the moon. It has many, many uses for lunar bases, for propulsion systems, for industrial activities on the moon, but absolutely for propellant. So excellent question, and the short answer is an enthusiastic yes.
Okay, that's all we have time for today. I want to thank everyone for joining us today, including our participants. We do have 2 other media teleconferences this week to talk about the additional payloads flying on Artemis 1, some inside Orion, as well as additional CubeSats that we did not discuss today. The next one up is at noon Eastern time tomorrow, where we'll discuss technology demonstrations. And if you missed it earlier today, NASA is also now targeting tomorrow, August 16th, at 9 p.m. Eastern to begin rolling the Artemis 1 rocket and spacecraft to the launch pad. You can find more about all of these payloads as well as the Artemis 1 mission at nasa.gov/Artemis-1. Thank you.
That concludes today's conference. Thank you for your participation. You may disconnect at this time.